George is getting queued up. This is George Milne. His presentation is going to be using wildfire prediction technology on the fire ground. When he gets ready and IT gets him ready, I'll let him take over. Thank you all.
Okay, and now for something a little bit different. We're going to talk about fire prediction. This is work I've been doing in Australia for quite a long time. I got some seed funding a long time ago from the Country Fire Service in South Australia, so I'm forever sort of grateful to them. What we do is we predict where a fire is going using the main drivers of fire spread: fuel, topography, weather, rate of spread models. What we're trying to do is find out where a fire is going to go in the future and alert communities so that we can give them early warning to get out if that's necessary. The system computes very, very fast. We can generate predictions for large areas in less than a minute. This allows us to be able to, or a skilled user, to be able to run these scenarios in worst-case scenarios. They can look at stronger winds, wind shifts coming in earlier. The technology has also been used to look at prescribed burning over long-term horizons, over 30, 40-year horizons, with the goal of trying to optimize fuel reduction strategies. How frequently do you burn? Where should you burn? The size of areas that you burn. But I'm not going to talk about that. So what I want to do is start by an actual example of us running a simulation. So this is a piece of landscape south of Perth in Western Australia. This is a forested area. We've got an escarpment running down here. This is generally farming areas. This is actually a bauxite refinery used in part of the process of making aluminium. This is a fire perimeter at a particular time of the day, 8 in the morning. 7th of January last year, 8 in the morning. Here's basically some information about what the weather is. And what we've done here is, this is the actual perimeter of this fire. The fire started up here with a lightning strike the day before, and it developed down here with an easterly wind. There was another lightning strike about here. That was controlled and that was put out. So the next morning, this is where the fire perimeter was. The fire had died down overnight, which is quite common. The wind had dropped, the humidity has risen. But 8 in the morning, we're simulating this fire using the forecast weather at 8 in the morning. So the Bureau of Meteorology has given a specific forecast for this location for the coming day. And we'll just run it for you. I've got lots of slides here, but they run quickly. So there's the simulated perimeter a little bit later. So this is 9 in the morning, so we're looking at hourly intervals. And we run it again. Another hour, another hour. There's a wind arrow so you can see what's happening with the wind. So this is a hot, dry, northeasterly wind. Now, if you know the geography of Australia, you've got nothing much up here. This is desert, very hot, and a hot wind blowing in, low humidity. And there's the fire developing. And it develops like this. And you can see pretty sort of standard stuff. Relative humidity is 20%. And this is the forecast weather. So this talk is advocating the use of a particular prediction technology. that is available. And here it is showing outside this little community here at 5 o'clock in the afternoon. And this is it at 6 o'clock in the afternoon. So this is in the morning. At 8 in the morning, this simulation is generated in less than a minute. And we can see that it gets to this community here. The fire does not run through here because this is an industrial site. There's no fuel there to carry it. So you can see the fire develops in 2 fingerings. And simulation is very, very close to what the actual fire did. But this is on forecast weather, not actual weather. Now, and there it is. It's well and truly in this little community here called Yarloop. And then this is what happened in that little community at 7:15 in the evening. So I think more than 70 properties were burned out and 2 lives were lost. So what does this tell us? This tells us that the technology has some potential for predicting where the fire is going to go. This is saying that if this had been used with a forecast weather at 8 in the morning, there would have been a 10-hour window to make sure everyone's out of this community, and perhaps even putting containment lines in, because you can see on the geography here, this is the community here, containment lines could have been built there with bulldozers. So what we've done here, and then what we also did was, there was a very detailed fire behavior investigation of this fire and a map generated of the steps of the fire perimeters. And we've been able to show that our simulation maps, using actual weather, maps that really well. So what I'm now going to do is just give you a quick overview of how this technology works. We suck in all the data, I mentioned that earlier. We run it through the prediction software, which calculates how the fire develops over the landscape. And that means potentially we can send out warnings to evacuate communities. Not very complex. There is quite a lot of stuff going on in the simulator core, however, and I'll give you just a couple of slides to give you an idea of what's happened. One thing you should note is that Western Australia is large. These are to scale. Western Australia runs from the north of Scotland, if you know where Scotland is, down to about here. So, throughout the year there are fires burning. Because that's tropical savanna at the north and temperate woodland in the south. The system is currently used centrally by Fire and Emergency Services Department in Perth, but there are difficulties in them running it when there are multiple large fires running simultaneously, because most of our fires are caused by lightning strikes. Sometimes you might have 20, 30, 40 fires quite spread out. There's problems of them running it on multiple fires and then communicating it to fire crews on the ground. How do you get maps to fire crews that are 1,000 kilometers away? How can you communicate that to a fire truck? So, and most of the firefighting in Western Australia, in rural areas, outside the cities, is done by volunteer brigades, so I have 22,000 volunteers. Practically none of them are full-time employees. How we calculate the spread of fire is we discretize the landscape into polygons. The key point is the distribution of the centroids, the central points. And the basic algorithm, it says that once we know when one cell ignites, and we take that to be uniform, we calculate the neighboring cell's times of ignition relative to that, according to fuel type, fuel load, slope, aspect of slope to a prevailing wind, and wind speed. And for example, here's a sort of front moving in that direction with the wind in this direction. These are burnt out, these are burning cells, and we calculate the time that these ignite relative to the times that the burning ones have ignited. And this is classic computer science, if you like. I'm a computer scientist and mathematician, discrete event simulation. So we're doing this discretely. The landscape's discretized, and then we're getting these time stamps of when the cells ignite. And we put them on an event queue, and we compute them left to right. This is actually a very fast computation process. What we can do then is we can run the system without internet connection. We can load it onto a tablet. We can preload all the geographical layers we need, and the rate of spread models. And then all the user has to do is put in the current fire perimeter or the lightning strike locations. They can do that with a stylus on the screen of the tablet, and then put in the forecast weather. They get it over the radio, and they can put in wind speed, direction, temperature and humidity using graphics on the screen. And we've got this running well on a Microsoft Surface. So it's very fast simulation. It allows predictions to be generated quickly. The traditional approach in Western Australia was to do this manually by hand by looking up tables and then calculating how fire would spread in different fuel types and drawing it on maps. Because it's so quick, we can do what-if scenarios. So we can use the forecast weather, and then we can have a worst-case scenario, and we can work out different scenarios and work out which communities are at risk, and hopefully get early warning to evacuate them. Just to give you an idea, a simulation we've done of a fire that ran for 100 kilometers. It's got about 70,000 cells. The computation takes 10 seconds, and drawing the fire perimeter takes 20, so that's less than a minute. Here's an example of it running in a fictitious fire. This to give you a bit of an idea. This is obviously a satellite image. There's really two key fuel types here. There's native vegetation, which is a type of eucalypt, burns fairly slowly relative to the farmlands, which are fields. They'll either have grain crops on it or they'll have grass. And we have these layers are all pre-produced. So there's the two fuel types that are relevant. We use two different rate of spread models for the native vegetation, which is now the orange color, and grassland. And here's a fire just running, and I'll just run through it. We've put in a fire perimeter at a certain time. We have a weather sequence that we've put in. Standard weather in this part of Western Australia in summer is a northwesterly swinging around to the southwest and coming in from the ocean. There's it running here. And you can see the fire's running faster in the grassland than in the native vegetation, so you're getting these indentations because of the different speeds, rates of spread. And then the wind swings to the west, and then it swings to the southwest. Again, you can see it slows down in the native vegetation, runs very fast through the grassland. There's actually a community here, so you can then see what time the fire would get to this community. If this was the forecast weather, you can then say, well, look, you need to get out of here and you need to go on a safe route. You need to go up this road, not down this one or not that one. So it gives you this feel for how a fire develops through time. Here's another one that happened about the same time as the first one. And just to give you an idea of what we've done, we've tried to use good historical data of fires and validated this technology against this known data. So this is our simulation of a fire. This is the south coast of Western Australia, town of Esperance. Lightning strikes, this is native vegetation. Lightning strikes in here, the fire burnt for a few days, and this is the perimeter in the morning. These are all fields. This is one of the main wheat and barley growing regions actually of the world. So Western Australia is one of the world's biggest wheat and barley exporters. This is all paddocks. This is 100 kilometers, okay? And this was a fire in November 2 years ago. Most of the grain had not been harvested, and that was the final fire perimeter. And that was the actual fire scar. You can see the scale's a bit different, but it's approximately the same shape. This was the location where 4 people died, and the fire went from there to here in about 6 hours. And that's approximately 100 kilometers. So it gives you some idea of the speed of the fire. So the thing here is, could we have forewarned the people here? Well, we probably could have done a little bit better. The fire stopped dead running in this direction because the Southern Ocean's here, and really, really humid wind was blown in here when the wind direction changed, because the fire ran down from here and then changed 90 degrees and ran up this way, and then it was killed by the high humidity and the cooler temperatures from the ocean. That's all I want to say. How am I doing for time?
George, you exceeded operational expectations. So we have time for questions, and we also want to get a little more in sync with next door. So we're going to give you a 5-minute break after any questions that you might have on forecasting for George. I have the microphone and can pass it around. Questions? Yes, sir. Come around this way. You are?
Domingos Viegas from Portugal. Thank you, George, for your talk. I'd like to ask two things. Does your model accounts for spot fires? I assume no, because you are using Rotterdam, so it doesn't account for spotting. That's the first question. Second, I noticed that in some of your simulations, you had lots of islands. Is that due to vegetation or to some other?
Okay, so I'll start with the second question first. In some of these simulations, we get these island effects with the perimeters. What that is two quite different vegetation types. The islands, or the peninsulas, if you like, are caused by much slower burning native vegetation compared to the grassland or the cereal crop fires, which have quite different rates of spread. So you get the fire slowing down in the forested vegetation and then speeding up in basically the fields. And that's very common in Australia, and that is a big contributing factor, this different rates of spread in the sort of two extreme fuel type extremes. And that catches people out, and that's what often leads to deaths, because people know there's a fire burning, but they have no concept that it's going to move so quickly when it gets into the grasslands, which are completely dry in all these fires, or even the cereal crops. So wheat and barley, either crops or stubble, will have no moisture content in them at all in these fires, so the fire moves very, very quickly. And some of the speed, it's known that some of the speeds in this fire exceeded 20 kilometers an hour. And of course in this fire there's no native vegetation in here, so it raced through there. In fact, it was heading down to Esperance, just south, and it was forecast to be this change, but if the wind hadn't changed, it would have hit this town here. And this is all farming. In fact, when this fire happened, the fields were not green at all. They were brown because the grain was completely dry, ready to be harvested and sent off to wherever it gets sent off to. The first question was spotting. We do have a spotting model for some of these fuel types, some of the eucalypts, but that's very dependent on the type of native vegetation, whether it spots or not. I think the data on that isn't terribly good. We've got data on some of the fuels here. So these are Australian species of eucalypts, and some of them have bark that comes off very easily in summer and can be lofted and carry the fire downwind. These fires here, of course, didn't really have that effect here, other than the fact that the fire would have spotted out into the paddocks here and ignited. Some of our rate of spread models have that built into it. Above a certain wind speed, we can get spotting. So for a particular tree species and a particular wind speed, we have a certain spotting. But we don't put too much reliance on that, because it's quite difficult to understand whether a spot fire actually will ignite and the effect of that. If the ember goes downwind and doesn't take off when it lands, of course it's not going to have any effect. But so the answer to the question is it depends on the fuel type. Some fuels we think spot, but we don't have good data on it. That's the other problem. There's lots of gaps in our knowledge here. And the eucalypt species in Western Australia, of course, are quite different from those in the East Coast. There's I don't know if you know Australian geography, but there's a completely discontinuous, there's no connection between the forests here and the East Coast. There's no forests in between. There's this huge gap of nothingness in the middle of Australia. So thank you, Domingos.
Thank you, George.